welcome to the class. We had seen in last class about when it is concerned with the theoretical part, we had seen one of the components of the steam power plant as steam generator. We had also seen its different parts and mechanism of heat transfer. Now we are going to see the second component as steam turbine. But before going directly to the steam turbine, we are going to understand some basic concepts of compressible flows which are required in the phase of understanding of steam turbine. So let us start with that. So today's class is dedicated for stagnation conditions and nozzle flow. So in this case, first we have to make use of some relations which are called as standard one dimensional relations. But where are the applications of standard one dimensional relations? Since the fact is we are assuming that flow is having major variation in only one direction, and such flows are called as one dimensional flows. So what are the applications? One such application is flows with friction. So here we will have certain inlet in the duct, and then we will have certain outlet in the duct for the duct, and then due to the walls of the duct we will have friction. So there are certain losses due to friction, and then if we try to apply one dimensional relations for compressible flows, then we can try to estimate the properties at the outlet from the known conditions of the duct and the inlet. Then we have in some engines we have the flow through the engine where we have compressed gas or air in the combustion chamber, or where heat addition takes place. So here variation of the area in this fuel injection around would be not dominant, and further there is chemical reaction which is taking place, and that leads to the heat addition to the compressible flows. So we practically are going to consider the effect of heat addition onto the compressible one dimensional flows. That is one more application where we will try to get what is the outlet conditions in such a domain where heat addition is going to take place. Then we have one more relation or one more application where we have a blunt body and a supersonic flow flows over this blunt body, and as what we know, supersonic flow means flow having Mach number more than 1. In such cases there is a strong shock which is going to appear in front of the body, but very special is a streamline which is called as a stagnation streamline or the streamline, which is going to go from the center of the object when velocity is parallel to the center line. Then the variation for such specific streamline across the shock will be one dimensional only. So there are various specific applications where we can make use of the one dimensional relations. However, we in our case of steam turbines, we would be making use of these relations later on for few things that we will tell in detail in the following classes. But what are those assumptions which involve in knowing the one dimensional flows relations? And those assumptions include flow to be inviscid and flow is steady. And in some cases we will also assume that flow to be having no frictional work in these two cases, and here we will incorporate friction as not the term as what we are going to consider in some cases. But in general these are the two assumptions involved in deriving one dimensional relations and one dimensional inviscid flow relations with steady state particularly are these three, where we have this as mass conservation equation, this as momentum conservation equation, and this as energy conservation equation. And these three relations do not get directly applied to these three philosophies or three applications, but yes, these equations would with some specific extra terms would be eligible to get applied for these three situations. Hence we know that there are certain specific applications in which approximated one dimensional flow can be helpful to predict the flow properties. So now derivation for speed of sound. We always know that sound is a medium, or sound is a wave which is passing in a medium, and then that wave is having certain speed, and that wave speed which is having the infinitesimal changes in the medium due to the pressure variation, and those minute pressure variations are said to be the propagation of the speed, propagation of the sound, and then we are trying to derive the relation for speed of sound. So this is, suppose, the wave which is a sound wave. Actually it is traversing with certain velocity in a medium which is still, or which is having zero velocity, but we assume that the wave is standing still and the fluid which is given the velocity of the wave. So fluid is not stagnant, and now wave is stagnant. So there is wave which is stagnant, and then there will be fluid at station 1 coming into our control volume shown by dotted lines, and then there is fluid, the same fluid which would be leaving from the same control volume. So now we are going to understand how would be the speed of sound. Okay. So let us say that A is the velocity by which fluid is entering into the domain, and this A is practically our speed of sound, and this speed of sound is appearing here in the mass conservation equation, where we are saying that rho into A is constant, since we have area of the computational or area of our control volume is same, otherwise rho A u would have been constant. But momentum equation says that P plus rho A square is equal to constant, and then this equation, which is mass conservation equation, if we put 1 as inlet and 2 as outlet, but since we know that the speed of sound or sound wave leads to infinitesimal changes, and if there is A as speed, rho as density, P as pressure, and T as temperature at the inlet, then those quantities at the outlet would become A plus dA, rho plus d rho, P plus dP, and T plus dt. So this is the variation of properties across the sound wave. Then using these conditions we can put it in the mass conservation equation. Practically we mean over here that rho A at the inlet is equal to rho A at the outlet, but rho A at the outlet is rho plus d rho and A plus dA. So the same mass conservation equation as what we have said as constant between inlet and outlet is getting represented as rho A is equal to rho plus d rho into A plus dA. Then we can expand the bracket and then say that rho A plus rho dA plus A d rho plus dA d rho, but dA d rho would be, already dA is a small quantity, d rho is also a small quantity. So multiplication of two infinitesimal quantities would make their order of magnitude much lower than the other terms, and hence let us neglect this term to be out from the above expression. And then further we know that rho A can be cancelled, so we can get an expression which says that rho dA plus A d rho is equal to 0. So we get d rho by dA is equal to minus rho by A. So this is what we could achieve from the mass conservation equation across the sound wave. Further, let us apply momentum conservation equation across the sound wave. Momentum conservation equation says that P plus rho A square before the wave and after the wave are same. So P plus rho A square is before the wave, but P after the wave is P plus dP, and rho is rho plus d rho, and A u, and here we have basically A, and A plus dA bracket square. Then we can get here the same term, this bracket can be expanded and said that A square plus twice A dA plus dA square, and rest of the terms can be kept as same. Now we can, as neglected in earlier case, dA itself is a small quantity, so dA square will be further small. So let us neglect that, and then neglecting that we can write down the same expression without just dA square. Further, let us multiply these two brackets and say that rho A square, then we have twice A into rho dA, and then we have rho A square, then we have d rho A square, and then we have d rho into dA into twice A. So these are the 4 terms. Further, higher order terms dA d rho will be neglected here, and then we can get the same expression without the term of dA d rho. Now the same thing we can further, if we go, then we can neglect, we can cancel dP, we can cancel dA square, and then we can have only 3 terms in the expression and equal to 0. So we get 3 terms in the equation and equal to 0. Let us divide the terms by d rho, and we have dP by d rho plus twice A rho dA by d rho plus A square. But we know that from mass conservation equation d rho by dA is equal to minus rho A, minus rho upon A. So we can put this over here, which will be becoming minus A by rho. So we can further have rho cancelled, then this will be becoming minus twice A square, but we have plus A square. So basically it leads to dP by d rho minus A square is equal to 0. So this is the speed of sound expression, which says that A square is equal to dP by d rho. So A is equal to square root of dP by d rho. But here the changes are so small such that we can treat this as an isentropic condition, where practically dP by d rho is having variation of pressure with respect to density changes at constant entropy. But we know for the isentropic case we have P upon rho raised to gamma is equal to constant. So we can differentiate this and get dP by d rho, and that would give you as gamma under root gamma RT, under root gamma RT, since we have P is equal to rho RT. So this P can be replaced as rho RT, and then we can get the speed of sound expression as A is equal to gamma P by rho square root isentropic is equal to square root of gamma RT. So this tells that speed of sound in any medium depends upon the temperature. If temperature is high, then speed of sound would be higher. Obviously we are using these relations for gases, however this relation is valid in general. Now let us talk about stagnation quantities. So what do we mean by stagnation quantities? First of all, let us understand what do we mean by stagnation. Let us see, there are 3 situations in which first is there is a flow over an ogive shaped body, where we can see it is a low speed flow flowing over an ogive shaped body, and then this flow at point 1 has certain amount of velocity. When it comes closer to the body and when it hits the body at this point, very particular point, it gets 0 velocity. So such point is termed here as stagnation point. Here in the second example we have a vertical plate and flow is coming perpendicular direction to the plate, and then or flow is coming in the direction parallel to the area vector of the plate, such that when velocity vector hits over here, velocity streamline hits over here, we get a flow with 0 velocity, and here as well the same point is called as stagnation point. Similarly, there will be an aerofoil and flow over the aerofoil, where initially streamline would become stagnant at this point or get terminated at this point. So this is the leading edge stagnation point, and when the two streamlines meet over here, we have a second stagnation point, which is the trailing edge stagnation point. So, practically stagnate means we are meaning over here that velocity is 0 for the flow. So, when the flow is adiabatically stopped to 0 velocity, then such changes in the flow which are basically related to reversibility of such stopping leads to isentropic stopping of the flow to 0 velocity from its initial state. Hence, if the flow is stopped isentropically from its initial state to 0 velocity, then the corresponding conditions are called as stagnation or total conditions. So, if we have a streamline of the flow where flow has P pressure, T temperature and rho density, then it has V velocity, which is not 0. So, if velocity is not 0, then corresponding quantities are called as static quantities. So, we have static pressure, static temperature and static density. But now, if this flow is isentropically stopped, then at this point pressure, temperature and density are called as total or stagnation, and generally they are represented as P naught, T naught and rho naught. So, these are the stagnation quantities of the flow. So, we have static pressure, stagnation pressure or total pressure, static temperature, stagnation or total temperature. Now, we are supposed to find out the values of stagnation quantities if we feel that we know the static quantities, or other way we are trying to find out what is the relation between static and stagnation quantities. Such a relation is called as, such relations are called as isentropic relations. So, let us take the third equation as energy conservation equation for one dimensional case, which says that H1 plus V1 square by 2 is equal to H2 plus V2 square by 2, where flow is flowing between station 1 and station 2. We know that H is equal to Cp into T. So, H1 is equal to Cp into T1 plus V1 square by 2 is equal to Cp into T2 plus V2 square by 2. Our argument at this moment is Cp is constant for the fluid flow, and since it is a perfect gas with a constant Cp, it is called as calorically perfect gas. So, this relation, if we feel that we have brought the flow to the 0 velocity isentropically at station 2, then we will say that V2 is equal to 0 and corresponding temperature T2 is T naught, and which is a stagnation temperature. Then the expression becomes Cp into T1 plus V1 square by 2 is equal to Cp into T naught. But we know that Cp is equal to gamma r upon gamma minus 1. Therefore, we get gamma r T divided by gamma minus 1 plus V1 square by 2 is equal to gamma r T naught divided by gamma minus 1. After putting the expression for C1 in this energy equation form. Now, let us divide this equation by gamma RT divided by gamma minus 1. Practically, we are dividing by this term to the complete equation. Therefore, this term will be 1 and we will have gamma minus 1 in the numerator and gamma RT in the denominator. Same thing would happen to the right hand side as well. So, practically this gamma minus 1 and this gamma minus 1 will cancel, and we have gamma RT is equal to A square as what we have derived. So, V1 square upon A square is equal to M square, which is using the concept Mach number is equal to local speed of sound is equal to velocity of the fluid divided by local speed of sound. So, this is the definition of Mach number. Therefore, we get an expression which says that T naught upon T is equal to 1 plus gamma minus 1 by 2 m square. So here basically if we know static temperature and if we know Mach number of the flow, then we can know total temperature, or otherwise if we know total and static temperatures, then we can find out what is the Mach number of the flow. Further, here let us use the isentropic relation, which says that P2 by P1 is equal to T2 by T1 bracket raised to gamma upon gamma minus 1. Hence, as what we have said, that in case of stagnation conditions, we are feeling that flow is brought to the rest isentropically. So, we can use this relation to correlate the temperature ratio and pressure ratio between the static and stagnation quantities. So, this is stagnation pressure, stagnation temperature, static temperature, and these can be correlated using this expression, which way again we can correlate for the density at the stagnation point divided by static density using its relation with the total temperature divided by static temperature. Thus, we can see here that the ratio of total temperature to the static temperature, ratio of total pressure to the static pressure, or ratio of total density to the stagnation density, this ratio depends upon only Mach number and speed and the ratio of specific heats. So, if we put Mach number to be 1, if this Mach number is 1, then we get a special relation, which is the relation between total temperature and the sonic temperature. Here sonic condition is specifically denoted by star. Further, total pressure and static pressure, they can also be found out from Mach number, but if we put Mach number is equal to 1, then this relation also become a specific relation between total pressure and the sonic pressure. Similarly, density ratio between the total and the static at the sonic condition can be found out in the same way, and these starred quantities can be seen to have only dependence upon the specific heat ratio gamma, since we are putting a specific value of Mach number which is 1. Now, let us try to design an expression, or let us try to find out an expression which is expression for area and Mach number relation. Let us consider a duct which is having area A at the inlet, which is getting fluid flow with velocity u, density rho and pressure P. However, in the direction of the flow, duct is having varying area such that at outlet we have u plus du, rho plus d rho, P plus dP and A plus dA. Such condition is no more one dimensional, since here area is varying in two directions. Okay, area is varying in the direction of flow. That is why there are changes in the fluid properties in the direction of flow, and there are certain changes away from the or normal to the direction of flow. If the changes which are happening normal to the direction of flow, if they are small, then such flows are called as quasi one dimensional flows. So, let us try to derive the relation which is area Mach number from the perspective of quasi one dimensional relation. Now, earlier in one dimensional relation we had considered rho u is equal to constant, but now for quasi one dimensional or in general we will have rho into A into u is equal to constant. This relation tells to us that differential of rho A u is equal to 0. So, practically rho 1 u 1 A 1 is equal to rho 2 A 2 A 2. Also, we can differentiate this expression which is d rho u A is equal to 0, and then we can get u A into d rho plus rho u into dA plus rho A into du. So, this is the differentiation of expression corresponding to mass conservation equation. For quasi one dimensional equations, quasi one dimensional equation for momentum is this, where this term was not present when we were considering one dimensional relation, and it was PA is equal to rho, it was P plus rho u square is equal to constant, but now we have area variation. So, we have P1A1 plus rho 1 U1 square A1 plus area variation in the direction of the flow is equal to outlet pressure into area plus outlet rho u square into area. So, this expression in differential form can be written between inlet and outlet as PA plus rho u square A plus P dA. So, this is a dA variation of area in the direction of flow is equal to P dP plus ADA into ADA plus rho d rho plus U du bracket square into A plus dA. After expanding this term, and again as what we did in earlier case, neglecting the all terms which are second order terms, we can get an expression which will be AdP plus AU square d rho plus rho u square dA plus twice rho UA du. After multiplying by this expression is basically obtained after multiplying equation 2 by u. We have got this expression. Let us star this. Let us take this expression which is equation number 2 and multiply this equation completely both sides by u. So, 0 into u is 0, but these three terms would get multiplied by u, and then we have an expression which is rho u square dA, rho u square dA, this term plus rho u A du, rho u A du plus A u square d rho. So, these three terms would belong to equation number 2 after multiplying equation 2 by u. Further, this equation belongs to the modified form of this starred equation. Now, we can subtract these two equations from each other, and then we can get an equation which says that dP is equal to minus rho u du. So, this is what we will get from this expression when we subtract the u multiplied equation from the momentum equation. Now, we know that the energy equation for one dimensional relation is rho is h1 plus u1 v1 square by 2 is equal to h2 plus v2 square by 2. Here let us consider the similar expression where we are considering energy flux at the inlet plus energy flux at the outlet is equal to the reason for change in flux, and here we are only considering pressure forces. So, rho 1 into E1 plus V1 U1 square by 2 minus U1 into A1, that is for the inlet of this domain, where minus sign negates, minus sign tells that velocity vector and the area vector at the inlet, they are opposite to each other. Similarly, this term belongs to same energy flux at the outlet. This is the pressure into area into velocity at the inlet, this is pressure into area into velocity at the outlet. We will rearrange the terms in this expression. We would get rho 1 u1 a1 plus rho 1 u1 a1 in p1 u1 a1 plus rho 1 u1 a1 into e1 plus u1 square by 2 is equal to same two terms at the outlet. Dividing equation 1 by h, dividing by equation 1, this equation let us divide by equation number 1, which says that rho au is equal to constant. So, rho 1 a1 u1 is equal to rho 2 a2 u2, and now we can divide this expression completely. We can get here as rho 1 a1 u1. So, u1 u1 will get cancelled, a1 a1 will get cancelled, and rho 1 u1 a1. So, this term will be cancelled. Similarly, we will have this to be is equal to p2 into rho 2, and this will be cancel. So we have P1 upon rho 1 plus E1. So this P by rho plus E is basically H, and hence we will have an expression which states that H1 plus U1 square by 2 is equal to H2 plus U2 square by 2, which otherwise says that H plus U square by 2 is equal to constant, which also says that H naught is equal to constant. So if we differentiate this expression, then we get dH plus U du is equal to 0. Now let us try to find out what is the area Mach number relation. We now know that for Cauchy one dimensional case, rho u a is equal to constant is mass conservation equation. Let us take log and differentiate this equation, which says that d rho by rho plus du by u plus dA by A is equal to 0. But from momentum equation we know that dP is equal to rho u du. So we have dP by rho is equal to dP by d rho into d rho by rho, but that from momentum equation is equal to minus u du. So considering adiabatic in viscid flow, we have this term at isentropic case is equal to a square. So we get a square into d rho by rho is equal to minus u du. So we have d rho by rho is equal to minus u by a square into du. We will multiply numerator and denominator by u. So we will have minus m square into du by u, where we know that m is equal to u by a. Substituting this d rho by rho term in equation number 3, which is this, and then we can get dA by A is equal to m square minus 1 into du by u. So we have three things in our disposal. First is this dA by A is the area geometry variation, and now let us consider a converging section where dA by A is a negative term. So if this is a negative term, on left hand side we should have right hand side also to be a negative term. So for that term to be negative, let us consider the Mach number to be less than 1. So if Mach number is less than 1, then this term will be negative. Okay. If this term is negative, then we have to have total product to be negative, so this term becomes positive. That means when area is decreasing in a subsonic flow, velocity increases. So this becomes the nozzle for subsonic flows. Now let us take an example of supersonic flows or diverging section, and in case of diverging section like this, let us feel that Mach number at the inlet is more than 1. So Mach number at the outlet is more than 1. So this term will be positive. And now if dA by A is a positive number, then this term also needs to be positive. So this term will be positive if du is equal to positive. That means again diverging section acts as nozzle in case of supersonic flow. So converging section acts as nozzle for subsonic flow, and diverging section acts as nozzle for supersonic flow. Further, if we add converging and diverging section together, then we have convergent divergent nozzle, which acts as nozzle, where at the inlet we have subsonic flow and at the outlet we have supersonic flow. So what we can see over here, that the variation of fluid flow properties across the duct depends upon the Mach number. So if Mach number is less than 1, and Mach number less than 1 means velocity of the flow is less than the local speed of sound, means flow is subsonic. So, for such subsonic flows we have convergent section as nozzles. So, we have three things here, we have converging section and we have diverging section. So, and we have nozzle and we have diffuser. Okay. So, converging section for nozzle and converging section, this combination is going to suit for subsonic part or subsonic flow. So, in the subsonic flow converging section acts as nozzle, but in case of supersonic flow converging section acts as diffuser. In the similar line we have supersonic flow which acts as nozzle when we have diverging section. Similarly, supersonic flow. So, since the fluid flow variation depends upon Mach number, we have some criteria which says that we have, suppose we have nozzle, then this nozzle will be converging section if the flow is subsonic, and this nozzle will be diverging section if the flow is supersonic. Similarly, we have diffuser, and then this diffuser will be converging section if the flow is supersonic, but this diffuser is diverging portion if the flow is subsonic. So, nozzle and diffuser, these two are the philosophies where flow is going to have certain fixed variation of pressure and velocity. In case of nozzle, velocity will increase and pressure will decrease, and in case of diffuser, pressure will increase and velocity will decrease. So, this equation says that converging section for subsonic flow acts as nozzle, diverging portion for supersonic flow acts as nozzle, converging portion for supersonic flow acts as diffuser, and diverging portion for subsonic flow acts as diffuser. Rest of the relations and their derivations we will see in the next class. Thank you.